Hello, Professor. This is my assignment 4 for Comp 3132. My name is Gurmesh, student ID 101471817. The first cell is just my imports. Here I'm defining the class names for CIFAR 10, airplane, automobile, bird, cat, deer, dog, frog, horse, ship, truck. Then I load the dataset. Keras gives it to me already split into training and test sets. I print the shapes so you can see 50,000 training images and 10,000 test images, each 32 by 32 with 3 color channels. In this cell, this is where I do data preparation. First, I divide both training and test images by 255 to normalize pixel value from 0 to 55 down to 0 to 1. That's standard pre-processing. It helps training to be more stable. Then I do my train val test split. I take the last 10,000 samples from the training set and use those of my validation set. So now I have 40,000 for training, 10,000 for validation, and 10,000 for test. The validation set is what I use to monitor the model during training. Tests stays hidden till the end. One hot encoding. Here I am one hot encoding all three label sets. So instead of the label being the number 3 for cat, it becomes a vector. I need this because I'm using categorical cross entropy as my loss function. Uh, just a quick visualization. I am plotting the first 10 images from the training set with the class names as titles just to confirm the data loaded properly. So model 1 is my over parameterized model. It designs on purpose to overfit. I've got two convolution blocks. First block is two conv 2D layers with 64 filters each, followed by max pooling. Second block is two conv 2D layer with 128 filters each, again followed by max pooling. Then I flatten and go into two huge dense layers, 1024 neurons, then 5112, 512, and finally the output layer with 10 neurons and softmax. Now I fit model 1 30 epochs batch size 128 passing in the validation test so I can track val accuracy during training. This is where you'll see the overfitting happen live if you watch the epoch sprint. Uh, this is Graph 1 shows accuracy. The blue line is training accuracy, the red dashed line is validation. You can clearly see training accuracy keeps climbing, but validation flattens out. The gap between them is the overfitting gap. Graph 2 shows loss. Training loss goes down nicely, but validation loss actually starts climbing back up after a few epochs. That's the classic overfitting signature. The model is memorizing the training data. Model 2 is the same architect as Model 1 but with dropout added. I put 25% dropout after each of the two polling blocks and 50% dropout before the output layer. What dropout does is during each training step, it randomly turns off a percentage of neurons so the network can't rely too heavily on any specific neuron. This is the same training configuration, 30 box batch size, 128, same validation data. And now look at the difference graph 3, the training and validation accuracy lines are way closer together than model 1. Graph 4, validation loss doesn't blow up the way it did before. Dropout is clearly helping the model generalize. Now, Model 3 uses L2 regularization instead of dropout. Same architect again, but now every layer has kernel regularization added. L2 works differently from dropout. It adds the penalty directly to the loss function based on how big the weights are. The bigger the weight, the bigger the penalty. This stops the model from overgrowing huge weights value, which is usually what causes overfitting. Now, training Model 3 again, 30 epochs, same setup. Model 3 graph. Training accuracy grows a bit slower here because the L2 penalty is slowing down weight growth, but the training and validation lines stay close together, so again less overfitting than Model 1. Data augmentation. Model 4 is the best one. It combines data augmentation with dropout, but first I'm showing what augmented images actually looks like here. Here I take the first training image and generate 7 augmented versions using random horizontal flips, shift rotation, and zooms. You can see the original on the left and the augmented versions on the right. Now I set up the image data generator for training, same augmentation settings, and the model itself is actually leaner than the others. So the model has fewer parameters overall than model 1, but it has more regularization built in plus data augmentation on top. Here I set up early stopping. It monitors validation loss, and if it doesn't improve for 8 epochs straight, it stops training and store the best weight it found. I fit up for up to 50 epochs, but it will usually stop earlier. Here it stopped at 39. Now, Model 4 graphs, training and validation accuracy are basically tracking each other. In this graph, validation loss follows training loss down smoothly instead of bouncing back up. This model is generalizing really well. Now, epoch analysis. This is my epoch analysis. I found the epoch where loss was lowest and mark it with green dashed line. That's the optimal stopping point. Before that point, the model is underfitting. After that point, it starts overfitting. Each stopping found this automatically, but the graph makes it very clearly visually. Now I evaluate all 4 models on test set the data. None of them have ever seen I print loss and accuracy for each. Now here's the bar chart comparison. Uh, Bar chart showing test accuracy for all 4 models. Model 1 is the lowest because it was overfitting. Model 2 with dropout. Model 3 with L2 are both higher. And Model 4 with augmentation and dropout is the highest. And that's my assignment for COM 3132.